Okay, it's a great pleasure to introduce my own colleague from Boston College, Professor Ziqiang Wang. He will tell us about superconductivity in Kagome systems. Welcome. Thank you.
Thank you. I'd like to thank the organizers for giving me this chance to share some recent development on the loop current charge density wave and what I would call a new type of a superconductor, Roton superconductor in Kagome metals. So I'm actually moving from 2D to quasi 2D. So I have a lot of people to thank. I'll actually skip this. Yeah, so you probably have heard of this class family of Kagome metals, 135, vanadium-based 135. There are three members in this family, three different alkaline metals, and they sit away from the Kagome plane, which is formed by the vanadium atoms. This is a perfect Kagome sheet. The antimony comes in both in the Kagome plane and above and below the triangles of the Kagome plane, sort of a coordinate the structure. They were discovered in 2019 when these people were looking for Zintel and Timonite thermoelectrics, and they accidentally discovered this family of Kagome metals, which are exfoliable, and it's the first time we have a perfect Kagome lattice stacking. So a year later, they found that this family of Kagome metals all show a CDW transition. Here it's shown for the cesium-based or the CVS. This is the heat capacity, resistivity, and the magnetic susceptibility. They all show an anomaly at 94 Kelvin. That's the CDW transition, and they vary within the family. The most important thing that I want you to focus on is above the CDW transition, you see the susceptibility is Pauli-like. It's a paramagnet. There are no local moments, any of those things. Okay, now at low temperatures, they all go into the superconducting state. And these are the temperature, Tc, for these three materials. And this is the heat capacity, resistivity, and the Meissner effect. Okay, so therefore, we've got a charge density wave superconductor. We see many of those in the TMDs as well. Sort of around this temperature, there is a CDW transition, and then a low temperature superconducting transition. But it turns out everything in between these two temperatures are actually quite anomalous. There is a class of phenomena that shows time reversal symmetry might be broken. I will concentrate on some of these. For example, the STM and laser STM shows that there is handedness response in the magnetic field, which is magnetic field switchable, the handedness, and there is also piezomagnetic response, indicating time reversal symmetry might be broken. And there are also these other techniques that are traditionally more powerful, probing directly time reversal symmetry breaking, and I think there are more evidence that that is true. And although there is also a controversy about whether there's some variations in the detection. There is another class of phenomena that's unusual that's related to rotation symmetry breaking and stripe order and electronic pneumaticity that I will actually not be talking about here. If the normal state is this anomalous, we know the superconductor is going to be strange. And indeed, it is quite strange and exciting. It coexists with charge density wave order. It's a multi-band or multi-gap superconductor. And it also turns out to break time reversal symmetry, probably inherited from the time reversal symmetry breaking already existing above the superconducting transition. And there is μSR, the superconducting diode effect that I'll describe a little bit. And more recently, there are sort of thermal Hall measurements that indicates time reversal symmetry is broken. And people have seen pair density wave formation in the superconducting state and pseudogap-like behaviors, both at low temperature above the upper critical field and at temperatures above Tc. Finally, I think this is perhaps the most exciting thing, is there are initial indications from quantum oscillations or little part type of oscillations that are charge 6e flux quantization, indicating the possibility of higher charge superconducting correlations existing in this superconductor. So it is really an extraordinary superconductor. We don't know if it's conventional or unconventional if we define it as electron-phonon driven or electron-electron interaction driven, but it shows extraordinary quantum phenomena. So my plan is the following. I'll focus on time reversal symmetry breaking. I'll describe some of the most recent experiments that's published this year. And then I'll try to convey a plausible theoretical picture for this whole phenomena may be describable by loop current order. So everything began, this unconventional charge density wave state began with this work in 2021. So if we look at, this is STM, so I'm the first one to mention the STM experiments. I guess these things are hard to do when you have a heterostructure. But these are bulk materials, so STM has made quite a lot of advances here. So if you, at higher temperature above the CDW transition, this is the topography, you'll just see 6 Bragg peaks. But if you go to low temperatures, then there are these additional 6 peaks coming in at half of the Bragg wave vector. So in all directions, so these are 2x2 CDWs. And they also show up in the conductance map, which I won't say much about. And there is a gap opening, as you can see. The CDW gap is about 50 millivolts, and all these are consistent with XRD and RPES measurement. There's something that's quite unusual, and it's the first time people paid attention to this. That is, if you look at the 6 CDW peaks in your Fourier transform of the conductance map, right? There are 6 spots here. They are of different heights. And in fact, they break all mirror symmetry. So these two, for example, will always be the same height. But if you use this as a mirror plane and do a reflection, they break that. So if all mirrors are broken, you know there is a handedness. And this case here, you go from the smallest in height to the tallest one, there is a left-handedness. So at the time, we thought this probably says this is chiral. But that word is so abused, we simply meant that there is a handedness you can define for the height of the conductance peak. And that you can get these kind of things just from the crystal structure. This doesn't say much more. But what's really interesting is this handedness changes if you apply magnetic field. This is in plus 2 Tesla. It's left-handed. And if you turn it to minus 2 Tesla, flip the field, and the handedness turns. So that means this kind of chirality somehow couples to the magnetic field along the c-axis. And so this is really, if this is true, then time reversal symmetry should be broken. So made a conjecture that because this thing is non-magnetic, right, it's paramagnetic, so maybe there is an exotic way of breaking time reversal symmetry, and we thought maybe it's due to a complex charge density wave or a charge density wave that involves persistent current ordering. I should mention my colleague Ilya Zakovich at Boston College, and he looked at the same material. He did also in STM. He finds that rotation symmetry is broken, but there is no chirality or magnetic field switching. So after that, there is a lot of controversy going on whether this result holds or not, and also there is Kerr rotation measurements. Some indicates there is a non-trivial Kerr rotation, therefore time reversal symmetry is broken, but there are other experiments that says no, they don't see a net rotation. So the field was actually, whether time reversal symmetry breaking or whether this kind of interpretation is correct was actually the question for quite a while. So this is probably in June. There is a paper coming out of Vidya Madhavan's group from UIUC. She brought laser beam in between the STM tip and the sample. And what she did is, the first thing, she did 2 things. The first thing is she showed that the polarization direction of the laser beam can be along any of these Q directions. These are the CDW Qs. And she will leave out this direction because, as I said, there is a unidirectional charge ordering, a stripe order in this direction. So that direction is not manipulable. But she can change the polarization in these two directions. And what she showed is she can actually tune the chirality of the CDW state. Right? So this is the case where there is no laser beam shine, there is a chirality. So she repeated the Princeton group result now for the rubidium compound. There is
this a laser on while you're cycling temperature?
Sorry, laser on.
While you cycle temperature?
No, it's just laser pulse.
Okay.
Yeah, and then you wait, and it's stable. After that, you can go home and come back the next day. The sample is in that state. So this one is without field. So let's say it's left-handed. And then she has this laser beam coming in with a polarization direction along B direction, right? So along this direction. And you make the Bragg peaks or the CDW peaks in B direction now higher, right? So you actually flip the chirality. And the other direction becomes smaller. There is a shear kind of tuning that you can do to make the peak height change. And then after a while, you can apply the pulse now with polarization direction along C direction. Then you make the C direction Bragg peaks, CDW peaks higher, so the chirality can change back. And you can do this sequentially at your own will, actually, and you can tune the chirality. Here, what's plotted is the relative intensity between B direction and C direction, and you can tune that by the sequence of illumination, right? Yeah?
Does it require critical power?
Yes, there is a critical fluence requirement. You got to go above that, and the laser is 1,000 nanometer laser with 1.2 volt laser. Okay, now the real breakthrough, I think, came when they actually looked at what happened to the position of the Bragg peak. Before we were talking about the height, but if you actually go in and measure down to a single pixel the location of the CDW Q, it turns out those are changing. That's the reason these heights are changing. So what happens is, so this is the ratio of the Qs in these two directions. And that will follow the polarization direction of the laser beam. In other words, maybe this one summarizes it better. If the field is polarized along QC direction, then the Q, the wave vector, CDW wave vector in this direction expands, and the other direction contract. And that's deterministically determined. So there is really an electric field switching of the chirality, right? And that has to be because of the laser-induced lattice strain. In fact, this is a nonlinear electrostriction effect, right? The electric field is actually changing the lattice. Okay, so we know actually what this height changing, what that means, this chirality, what that means. It really means the Qs are different. The ordering wave vector is different. But this does not say anything about whether time reversal symmetry is broken. So now she brings in the magnetic field and asks whether the same effect is seen when you apply a field. Now, usually what people do is a nonlinear term.
Just quick question.
Oh, sorry, I didn't see you.
The peaks do change heights, or they don't?
They do.
Or it's the sampling on pixels. You said that?
Oh, the peaks change location. And that's why the height is changing. So go back to here. Yeah, this summarizes. So if I have the field polarized along this direction, the actual Q value is expanding along this direction, QC. And then the intensity, the Fourier peak height increases.
And that's after the laser has been turned off.
After the laser has been turned off. Yeah, as I said, you can pause and you can wait for quite a bit of time, and it stays in that state. Yeah.
So it stayed in that state permanently?
Almost permanently. You can go home, and what they said is you can go home and come back next day, do the measurement, will be still there. Yeah. I don't know how long it will relax, but these, yeah.
I don't mean to take up time here, but there's some fundamental thing which I don't think is clear. The peak shifts.
Yeah. and the height increase.
It made it sound like because it shifts, then it changes.
Oh, this is just empirical. The peak shifts and the height changes. Yeah, at the same time. And in the other direction, it contracts and the height reduces in this direction. Right? So it's a shear strain. Yeah. Okay, so let's apply magnetic field and see if this really has time reversal symmetry breaking encoded in it. So usually people talk about magnetostriction, which is a nonlinear effect that involves two powers of B. So it doesn't break time reversal symmetry. And this is some stress-induced strain. We all know in 57, Jaruzelski pointed out, actually you can have a term that's linear in B. And the coefficient is the piezomagnetic tensor. And if this piezomagnetic tensor is not equal to 0, then you have a term that's linear in B, and that breaks time reversal symmetry. Right? So they did the same thing, this time without laser, just magnetic field, but they can actually get down to single pixels, finding the location of the Bragg or the CDW peak, CDW momentum. And it turns out this location or the position of the Bragg, the Fourier transform, the Q of the CDW, indeed moves with the magnetic field. Right? So maybe this is clearer. You put it in, well, you change the field direction. So maybe we'll still look at here. The ratio of these two Qs change from, well, flips around 0, right, when you flip the field direction. So maybe yeah, here. This is more transparent. So if B field is greater than 0, then QB, so this direction Q increases and intensity goes up. The height of the peak goes up. If you flip the field direction, then the opposite is true. Right? So this says there is a linear coupling here, and it's a piezomagnetic switching of the chirality. That really indicates spontaneous time reversal symmetry breaking. Yeah.
Is this also permanent or has very long relaxation time if you
turn off the field? That I don't know. Maybe it's in the paper, but I can't remember that. But these measurements were done in the field. Yeah.
Yes, I understand. When you apply a magnetic field, you use piezomagnetic response.
Yeah.
But when you get rid of when there's no magnetic field applied, is there spontaneous kind of this chirality?
Yes, that was the very first measurement, right? When you have no field, no laser, there is a chirality, right? So, so this supports there might be a loop current order that actually breaks time reversal symmetry, and we propose a particular kind of loop current order that is consistent with these sets of measurement. Okay. Now, this is still the same this year. This is probably in July or August. Jia Xingyin, the same person who did the measurement when he was at Princeton, now he looked into the superconducting state, still looking at this kind of chiral response in the density wave peaks. It turns out, as I said, the superconductor coexists with the CDW. So if you look at the superconducting gap, this is using a normal tip. This is the topography. This is a map of the superconducting gap, right? You measure peak-to-peak distance using STM. And you take a Fourier transform of this gap map, you will find there are peaks at half of the Bragg vector, so at the CDW vector. So the gap modulates with the CDW momentum, right? And once it modulates, you can do Fourier transform, and you find these intensity peaks, again, shows this kind of chirality. For example, going from weak to strong, this one is right-handed, right? So indicating the superconducting state may also break time reversal symmetry consistently as what you've seen in the CDW state. Now this one is done with the superconducting tip instead of the normal tip, right? So then the superconducting tip will give you the same result, just to say that this is really indeed a superconducting effect. This is also the same year, this year. This one was probably in April or May. This is a group from Westlake University in China, Ling Xiao's group. What they did is they measured the superconducting diode effect in zero magnetic field. So in other words, you measure the critical current along one direction, and then you flip the direction, and you measure the critical current. And they are not the same. And that requires broken time reversal symmetry, as indicated here. I won't go into these details. And it turns out the polarity of the diode depends on thermal history. That makes it kind of more convincing that it is a time reversal symmetry breaking, spontaneous time reversal symmetry breaking effect. They also looked at quantum oscillations, and they see quantum oscillations, which is really hard to understand, which they interpret as these boundaries, these chiral domains. This is a chiral superconductor, and these chiral domains may have formed a loop so that you see quantum oscillations of that kind. Okay. Now I come to this fourth experiment this year. This paper eventually got published in PRX this year, but the result was around for maybe 2 years. And they took the cesium-based compound and exfoliated into flakes, and the thickness is about this much. So this is about 15 to 20 layers thick, right? And then they punched a hole using focused ion beam, and that device is shown here. Now, this is an RT curve of this device, and you see that there is a huge fluctuation region, right? This is TC onset, and this is zero resistance temperature. There is huge fluctuation, and there are actually structures in this region. All right, and the area of the hole runs from very small to about a micron. Okay, now what you want to do, well, the title says you're looking for charge 6E flux quantization, is you now apply a magnetic field and do resistance measurements and look for oscillations, right? But you know you're not going to see traditional little Parks oscillation, because that actually requires you to have a very sharp transition, right? And this is crazy. This is so broad. But they nevertheless tried it. And what happens, I've summarized it in this figure, as you go down from the TC onset, you see these oscillations, and you plot these periods of the oscillation here. You see this is h over 6e. Right? And then you cool down in temperature, it changes to h over 4e. And then at very low temperature, you'd have to apply a strong enough field to actually go below TC to make these states normal, and then you see the 2E oscillations. But this is repeated in about 5 samples, 5 devices, and every time you need to use the inner hole area of this device to figure out the flux. It's consistent area figuring out all 3 of those. And this had been a puzzle for quite a while until Patrick Lee and Junhong Han wrote a theory paper saying that if you're in the strongly fluctuating regime, then indeed the trajectory is to hug the inner hole so that you reduce the fluctuations, and supporting that this indeed is consistent with the picture of 6E and 4E flux quantization. But that's still not convincing enough. The questions that they got from the referees had always been that you don't know exactly what would be the area, right? Because it's not a thin-walled device. So eventually they made this device, which is very large, 1 micron in size, and the wall is thinner than in this case. The 6E oscillations is calculated with this area. Same thing for the 2E. Now, if you think these oscillations, this is not 6E, but 2E, you really would have to use an area that is bigger than the dimension of the device. So that says that the 6E oscillations indeed is not 2E. Okay, so that's the basic recent development. How much time do we have? 5 minutes? 5 to 8 minutes also. Okay, I'm going to run fast. Um, so we have a picture that says made in the normal, in the CDW state, there are low loop current order. And these are loop current metals, so they are Chern metals. They are not Chern insulators, they are doped Chern insulators. And these Chern Fermi pockets can be responsible for some of these anomalous Hall effect and orbital magnetic moments. And I would argue once you have a loop current running, these are persistent current running in the CDW state. Then if you go to the superconducting state, these loop currents can become loop supercurrents, right? Because these are staggered currents. They're not uniform currents. Those are forbidden by Bloch theorem. But you have a loop current that varies on the atomic scale that goes into the superconductor become loop supercurrent. And this loop supercurrent will necessarily circle around vortices and anti-vortices, right? And therefore, there is a spontaneous nucleation of a vortex-anti-vortex lattice. And that is what I call a Roton superconductor, right? Because we know those vortices, a pair of vortex-anti-vortex is actually a Roton, right? Or pair density waves. And that can go through vestigial order if you melt the Roton superconductor and leading to higher charge superconductivity. If I really have no time, why don't I just say what is special? One page on what's special about the Kagome lattice and these materials is the Kagome lattice has 3 sublattices. All right, it's a lot more than 2. Okay, but it's a lot less than Marie. Right? The other thing that's special is these materials will have the Fermi energy quite close to this Van Hoff singularity. And Kagome has a very dramatic sublattice effect, which is new physics, that is at this Van Hoff points, these quantum states only reside on one set of sublattice. So it's sublattice polarized Van Hoff states. And because of that, if you want to use this Van Hoff singularity to form a density wave, you have to use 2 different sublattices, which means your density waves are going to be on the bound, not on the site. Right? And also, it says the intersite Coulomb interaction now is much more important than the on-site Coulomb interaction. Right? Now, based on that, I can write down the CDW Hamiltonian here. These are just the bound variable. I give the Q, which are these nesting Qs, and then there is an amplitude in the front. And if this amplitude is real, you have real bound ordered CDW, and that's known as the Star of David for one sign, or the inverse Star of David, or the trihexagonal for a different sign. So it's the breathing of the Kagome lattice. But when this thing is complex, then you have currents running on the bound. Right? This is a loop current state. And it's a staggered current, as I emphasized. The net current in a unit cell is 0. Right? So it's an orbital antiferromagnet. It breaks time reversal symmetry and keeps inversion. And we all know these loop currents have been proposed for cuprates for quite a while. The very first one is 1988 by Ian Affleck and Brad Marston. And some of you have probably heard the sad news that Ian passed away this week. This was on Heisenberg model. We actually doped it to make it connection to cuprates, but there is a weak coupling version, which is called D-density waves. Again, loop currents. And the copper-oxygen loop currents for the cuprate pseudogap phase by Chandra Verma. So we actually took this loop current from this context. And interestingly, the same year that this was done for Heisenberg model, Duncan proposed the quantum anomalous Hall model, which is on the honeycomb lattice. It's also based on loop currents on the next nearest neighbor bound. Right? Okay, so now recently we have realized this state by looking at a microscopic model with hopping, just a single orbital with hopping and extended Coulomb interactions, both nearest neighbor and second nearest neighbor. I want to show this, that it turns out the nearest neighbor Coulomb interaction drives a real CDW, bound ordered CDW. And if the next nearest neighbor Coulomb interaction is strong, right, because of the sublattice interference effect, you generically get loop current state, loop current order. And this is stable away from half-filling as well. So if you are away from Van Hoff as well. If you're exactly on Van Hoff, you get an insulator. It's a Chern insulator with all these. It's the Haldane phase on the Kagome lattice. You get all these Chern bands. Right? However, the material is not exactly this multi-orbital, and the Van Hoff points are not exactly at the Fermi level. So you dope these things, and you get these pockets. And these are the Chern pockets that carries most of the Berry curvature, right, of the Chern bands. So you can account for some intrinsic anomalous Hall conductance and orbital moments, and they would respond to magnetic field. And people are actually looking for that in momentum space. These are moments in momentum space. And there are quantum oscillations showing there are indeed small pockets showing large Berry phases. And more recently, ARPES and STM measurement detects pockets in these locations. But we don't know if they are actually topologically non-trivial, so that needs CD ARPES probably. So I'm going to skip this. I'm just going to say a few words about what happens in the superconducting state. So the question that we encounter is a question I think we encounter in different material platforms, twisted and untwisted. It's a partially filled Chern bands, right? Here I draw these Chern bands, and here I move the Fermi level here, and I get 6 or 3 pockets, Chern pockets with concentrated Berry curvature. The question is, what would be the stable ground state? You could go with chiral quantum spin liquid or fractional quantum anomalous Hall effect we've heard already, or you can go with an intrinsic chiral topological superconductor. That's what I want to show to you. So basically, the reason I want to call it Roton superconductor is the condensation of this Roton mode, which I think F. London really made an insightful comment in 1946. London thinks this is short-range order on atomic scale. Right? That's really far insightful. So when this comes down to low energy, you would have order at this momentum, and you would have a Roton. Oh, then here is Allen's magneto-Roton in fractional quantum Hall effect. And okay, so when this condenses, you would get a Roton superfluid or Roton superconductor. And that indeed comes out of a macroscopic calculation with some pairing interactions between, a pairing attraction between nth nearest neighbors that we looked at. I'm going to skip these details and just tell you the result. The result is basically without loop current, you have a real representation of 3D of the cubic group. And in that case, the 111 state, right? You take these 3 order parameters, you make a 111 state with the same phase. That's the lowest energy. And you have 2 chiral states that's a degenerate representation, 2-dimensional, but they're at higher energy, carrying angular momentum plus or minus 2. But what happens is once there is a loop current, this Josephson coupling between the pocket acquires a phase. And then you go to the complex representation of the cubic group. There is no degeneracy. And if the Josephson phase is large enough, then you enter this Roton and anti-Roton superconducting state. Right? The ground state would be chiral, D plus ID with these values. And this shows that for all of these different pairing, nearest neighbor or second nearest neighbor or third pairing, you get these 120-degree chiral phases in a calculation. And the reason this is so robust and come in at even small loop current is because this phase is really related to a Berry phase of the permutation operator in the sublattice space. Right? And so, yeah. Okay, so this is the real space picture of the Roton superconductor. It's either a 1x1 or 2x2 because you've broken, the CDW has broken translation symmetry. And what I plotted here with arrows are the phases of the superconductor. you see this 120-degree phase winding, and it always has vortices and anti-vortices here, right? And that reminds us of the XY model, frustrated XY model on the Kagome lattice, which turns out to be very difficult to order because of fluctuations of chirality or vortices, right? This so-called vector chirality. And in fact, that explains why there is a huge fluctuating region and within which we might get charge 6E superconducting correlations, because you can form a composite order that actually sees no chiral phase. So that would survive and have its own KT transition. Okay, so I'll skip all of these. And this is my summary. So I think the Kagome lattice is really interesting. It's gone through a trilogy. And the first one that people studied was this insulating site on the spin liquid. And then there is a class of Kagome magnets, and ion tin was the pioneer there. And then finally, we've seen the non-magnetic superconductors that I spoke quickly today. So this is really a materials platform across the full spectrum of correlations, right, and topology with long-range entangled states and short-range ordered topological states. And thanks.
Thank you so much. Yeah, we already had a few questions. Let's take one short one, and we can discuss over the lunch.
Any Cooper pair beyond 2E is extremely rare. You claim you have one superconductor has charge 4E and 6E.
Yeah.
I find it is absolutely incredible.
Yeah, so actually, thanks for the question. Maybe I can say how it is easy to understand in this case. It's a multi-component superconductor. So the superconducting order parameter has some internal structure. Then you can have, so let me explain it using this. So we have these sets of pockets, right? They pair. They give you 3-component usual 2E superconductor. You can write down their coherent state wave function, right? And now let me expand this. If I expand this, I can see 2 kinds of contributions, right? This is the 2E term. By the way, even a BCS wave function contains pairs, 6E, 8E, right? It's just a coherent state of all pairs. So if you expand this, you wouldn't be surprised you'll see all of these. And this 6E has a unique property. It's the product of these 3. So these chiral phases cancel. Right? This term doesn't see the chiral phase. So if the chiral phase is strongly fluctuating, as we know it is true for the XY model, then I can kill all of these. So the 2E and 4E even can be killed. And what's left is this 6E term. You can re-exponentiate and get the wave function of the 6E. So that is what this vestigial order really means. In other words, you frustrate the 2E parts, and you let the residual parts take over, and you get higher charge correlations.
Okay, thank you. So lunchtime, Jiadong, do you want to say something about lunch?
Yeah, so I think we are running behind the schedule, so we come back at 1:45, and lunch is provided the other side of the wall.